Hi, I'm Steve Halladay. This is my 5th video on Raspberry Pi bare metal programming. You may recall in the previous video we wrote a small program that was a loop to blink the LED on the Raspberry Pi. We did this by encoding machine instructions in hexadecimal and then putting them into a hex editor. We found that that was a pretty painful way to program, and so what we're going to do in this video is build a small assembler. An assembler is a tool that allows you to work in mnemonics instead of binary or hexadecimal to do your programming at the machine level. It's a little bit easier to work with because the mnemonics are a little more meaningful to us as humans. One of the things that's interesting about programming languages is as you start out, the language focuses on the processor itself and on the machine. But as the languages become more and more advanced, they focus less and less on the machine and more on the model of the reality that you're trying to portray in the program. And so the assembler is the first step down this path. Let's start by investigating a grammar that I've outlined for our assembly language. The grammar that I've outlined isn't exactly like the grammar that you're going to see in the ARM instruction manual, for example. This grammar is a little bit simpler, and I don't do the full instruction set. All I'm doing is just enough instructions right now to be able to rewrite the program that we wrote in the last video, but write it in mnemonics. These types of diagrams I'm showing here are called recursive transition diagrams, or some people call them the friendly train track diagrams. And the way they work is that you follow the arrows here, and it shows you how you can build up constructs within the language. As you may recall from your computational theory class, a grammar is a set of rules for constructing legal sentences within a language, and a language is just a set of sentences. Here's how you read these recursive transition network diagrams. What we have here is the program, which is the top level construct in the grammar. And a program is made up of 0 or more instructions, as we see by this. So we could either go through this loop 0 times, or we can go through it 1 or as many times as we want. And each time we go through the loop, we accumulate another instruction in the program. An instruction, in turn, is defined as an optional label and an operation. So we see here that if we were coming along the train tracks here, we could turn left and go up and catch the label, or we could go straight and not have a label and just go straight to the operation. So we see how that works. A label, in turn, is made up of a name and a colon, and the name is an alpha character followed by an alphanumeric character, 0 or more of these, as you can see, and an alphanumeric character is either an alpha character or a digit. So basically what this means is we have to have an alpha character, and then we can have 0 or more alphas or digits. As we continue to look at the grammar, we see that an alpha is defined as the constants character A through Z, and digits are 0 through 9. We have a hex digit also, which we can define as a regular decimal digit, or it can be A through F. So the set of hex digits includes 0 through 9 and A through F. And then finally, we can use these constructs to build up the notion of a number, which can be either a decimal number or a hex number. The hex number starts with a 0x, and then it's followed by hex digits, while a decimal number is just a set of decimal digits. These are kind of the foundational pieces of the grammar, and not too exciting. Let's look on through the grammar. You'll recall back up here that an instruction is made up of a label and an operation. So let's look at what an operation is down here. An operation, for the grammar that I've defined here, may consist of either a branch operation, a data processing operation, or a load and store operation. So you can choose one of these 3 types of operations. And we'll look at each of these 3 in turn. A branch instruction consists of a constant B followed by a condition and then a name. And this condition would be these letters. It could be nothing, or it could be EQ, so the instruction would read BEQ, or just B, or BNE, and so on and so forth. The grammar only describes the syntax of the operation. It doesn't really describe what it means, and so I'll tell you a little bit about what it means as we go through here. A branch instruction, of course, as we saw, causes us to change the program counter in the processor. If I branch with no condition, then that's the same as branch always, which is BAL. So B and BAL are equivalent, but B is just a shortcut. If I do, for example, we'll see in our program BNE, this means branch when not equal. In other words, when the CPSR equality bit is not set. So these two together form what we would call the opcode for the operation. And then the name is the name of the label where we want to branch to. And you'll recall that we saw a name is just an alpha followed by alphanumerics. So that takes care of the branch. Now we'll look at the data processing instruction, then we'll look at the load and store instruction. Here's an example of how you would create a data processing instruction. I've only accounted for these 6 data processing instructions. You can recall that we could do an AND operation, and notice that all of these data processing operations can also have a condition code as well, which we saw back up here. And the condition code may be nothing, which means do it always, or it may be one of these conditions. So an AND operation might be followed by a condition and then 3 parameters, or a parms 3 I called it. The parms 3 would consist of a register, a register, a register, and a number. This first register in these types of operations is where the result gets stored, and this is one of the first parameters, and this is the second parameter. This extra number is the amount that you want to shift this register by. And you'll see that when you look up the data processing instruction in the ARM instruction manual. The data processing instruction has the destination register, which was the first register in my list, this RN, which is the first operand, which is the second register in my list, and then operand 2, which would be RM, and the amount that we want to shift. Okay, so that's how these instructions map to the mnemonics. Let's go back and look at the grammar some more. You can see that some of these data processing instructions only require 2 registers and a number. So this would be the destination register, this would be a parameter register, and this would also be the amount that you're going to shift this parameter register. I kind of skipped over this section here in both of these. The first thing in here, and I should have actually put this in quotes, this is an I. So for example, I might say AND I, A-N-D-I. Register 1 would be the destination register. Register 2 would be the value that I want to try and this number would be the number that I would be bitwise ANDing in with the value in this register, and I would store the result back in here. The same goes for this immediate path down here as well. And you'll notice down here that registers are just an R followed by 0 through 15. That's how I would indicate a register value. The load and store operation has this format to it. You'll have LDR or LDRB. The B means that I'm only moving a byte, whereas LDR means I'm moving a word. Followed by the condition again. And of course, if we leave the condition off, that means always. Store works just like load, only it's STR instead of LDR. Store the register value, or store the register's byte value. And then we have a sign parm. What that represents is one of these 2 paths here. And here's how you read this sign parameter. The first register in both these cases, and notice we have the immediate case again. In both these cases, this first register is the resultant value. So if we're storing, then this first register is the value that we're going to store. And if we're loading, this is where we will load the value. This second register here on the top line is the base register, as is the second register here as well. This is also the base register, meaning the base address in memory or the base device address. This third register is the offset amount. So what happens is we take the base register, we add the offset amount, and we go out and if we were loading, we would go out and get that value and stuff it into this destination register. And then the signed section here is a number. If you were to look at the ARM instruction set, you'll notice that this is an 8-bit value that allows us to shift this register one way or the other. The value isn't actually signed in the encoding, But there is an up and down bit, as you may recall, in that load encoding that allows you to make this effectively signed. And down here, the signed amount is an immediate offset amount. In other words, instead of taking the value that's in this register, we take this is a 12-bit value down here, and we add this to the value of this register, and that becomes the address that we're loading from memory. You'll notice that the signed mnemonic refers to either a negative number or just a number. To help you decode the grammar, it might be wise to get out your ARM instruction set manual and to kind of compare these different instructions that we've looked at, and they'll start to make a little more sense to you how you might encode the mnemonics that the grammar describes into the actual machine code. Now let's talk about how we actually build the assembler. It turns out that in programming languages, there's a lot of tradition that goes on. We've built compilers and assemblers a lot like we used to years ago when there was a lot of constraint in terms of memory and processing power, and so we still follow many of the same traditions that we built back then. There's maybe not as good a reason for that today, but a lot of times you'll still see people follow these same traditions. One of the traditions that we've come up with is to divide a programming language into two pieces, a tokenizer and then a parser and a generator. The tokenizer's job is to take characters and divide them up into tokens or small symbols, and then you get a stream of symbols. So our source code comes into the tokenizer, which is a stream of characters, and out comes a stream of symbols, things that have been divided up into pieces. These tokens, we'll talk about these here in a second, but these are kind of like words or maybe instructions, and you can define tokens to be pretty much whatever you want them to be. I've defined them fairly broadly in the example that I'm going to show you here. The other thing the tokenizer can do for you is it can remove comments from the code. It gets rid of extra white space and things like that. The parser generator then follows the grammar mostly as I described above in the transition network diagrams, and it reduces that grammar into instructions which can then be encoded, and we output that kernel.img file that we're so familiar with at this point. So let's take a look at how the tokenizer works. A tokenizer really is just a state machine. If you've studied computational theory, you'll know the state machine is a set of states that the machine transitions between states based on some input symbol. And so I've defined these 4 tokens. I've actually listed 5, but the comments don't actually emit any tokens. They just get consumed and get lost. But I've identified these 4 different tokens that my state machine is going to emit. So alphanumeric strings, special characters, decimal values, and hex values. And the special characters would be like a comma or a square bracket or something like that that I might use. And what I've described here in the transitions is how my state machine works. So my state machine consists of states A through I. I start in the initial state A, and if I get a white space, I move from state A to state A. That's how we read it. So a white space leaves us in state A. If I get an alpha character and I'm in state A, then I move to state B. If I'm in state A and I get a constant 0, I move to state C. A 1 through 9, I move to state E, and so on and so forth. So this shows me how I move through these different states. The way I developed this transition diagram was I kind of thought my way through it, drew out a state machine. I would have shown the state machine here, but it was pretty nasty and kind of hard to follow. And so I actually ended up building the state machine in pieces. These tildes over here mean if I'm in state A, for example, and I get an asterisk, then I reject the input. So anywhere I've got a tilde, I reject the input. These subscripts here, for example, if I'm in state B and I get a white space, then what I want to do is I want to emit a number 1 token, an alphanumeric token, and then move to state A. So these subscripts represent what I'm trying to emit into my token stream here, and you can see them throughout. A token, really, in terms of programming, consists of just some kind of a class that has a type to it. So it'd be one of these 4 types, and you also want to keep the actual value that allowed you to construct this token. So for example, if it's an alphanumeric, its type would be 1, and I would have a string that had the alpha characters with it. And same thing for the special character. I would have a type 2, and then I would have a single character that would be the special character that it recognized to generate this token. Here is the general form for the pseudocode for the tokenizer. I would implement it as an iterator, and so you have a has next that basically just checks to see if we're out of input symbols. And then the next operator actually goes and gets another token. The way that works is, while we don't have a token, we ratchet our way through the state machine. We get the next symbol from the input, which is a single character, and then we switch based on the current state. This is where we use the transition table that I showed you before. In a particular state, we might perform any action, which in this case probably we won't do much of anything, but this is the general form of a state machine. And then if the state is an accept state, then we would create an appropriate token that we would generate as part of the accept state, and then we calculate the next state, and then next time through the loop we'd be in the next state, and so on and so forth. And so that's basically all that the tokenizer does. It's pretty dumb, but it makes parsing into tokens very simple and very easy. Let's take a look at how the parser works. Here's the main for the parser. What we want to do is we want to create an array of 32-bit values that represent the instructions for kernel.img, and I'm going to call that array kernel.img. Eventually, when we're all done, we'll write that image out to the kernel file here, and that's what the last line in main does. Now, as you may recall from our syntax diagram, a program consists of 0 or more instructions, and that loop in the syntax diagram corresponds with this loop here in the pseudocode. What we're going to do is, while there are input tokens, we're going to parse instructions over and over. Now, how do we parse instructions? Well, that's down here. Should there be a syntax error anywhere along in parsing, the syntax error will manifest itself as an exception. We'll throw an exception, which we would catch down here, and then we'll print out the error message for that syntax error. Parsing an instruction consists of trying to parse a label and then parsing the operation. You'll recall from our syntax diagram that the label is optional, so we'll try to parse that, and if we can't find it, then we'll just go straight forward to parsing the operation. That try indicates that it may or may not happen. If it doesn't happen, we'll skip that and we'll go to just parsing the operation. Here's how we would try and parse a label. What we'll do is we'll take the first two tokens from the input stream. We'll call the first one label and we'll call the second one colon, and we'll set this default result value, which is what we're going to return, saying that yes, we did indeed parse a label. And you'll see that I return that down here. If we aren't able to parse a label, then we'll set this to false. If the label, meaning this token that we pulled out of the input stream, if it's an alphanumeric type, which a label should be, and if the colon is a special character, meaning this colon here is of type special character, and its value is actually a colon, then we know we have a label, and we can make an entry in the label table. The label table is a table that keeps track of the label's value and the location of where we are currently in the kernel.img array. That's so that we can figure out how to branch to this label. Should any of these conditions not be the case, if the first token is not an alphanumeric, or if the colon is a special character, or if it's not a special character that's actually a colon, then we aren't parsing a label. So what we need to do is we need to push the colon and the label back in the token input stream so that they can be used to try and parse the operation that's coming up. And we'll set the result to false, saying no, this wasn't a label. So that's how determining if we have a label or not. Now, parsing the operation consists of these three possibilities. You'll recall back here in the operation on the syntax diagram, it can be either branch, data processing, or load store type of instruction. And that's what this if else indicates for us. You'll notice that we try to parse a branch instruction. If we're unable to do that, then we try to parse the data processing instruction. And if we're unable to do that, then we'll try to parse a load store operation. And if it's not one of these three types of operations, we're going to throw a syntax error. Here's how we try and parse a branch instruction. I'm going to show you how to do this, and I'll leave these as kind of proof to the reader, so to speak. To parse the branch instruction, if we go back and look at the syntax diagram one more time, we notice that the branch instruction consists of a B, a condition code, which could be nothing, or it could be AL, or it could be NE. So this would be BAL or BNE or whatever is a valid branch operation, followed by a name, which is actually the name associated with the label that we're branching to. So to parse the branch operation, we'll pull the next token off and we'll call that an operation. We'll pull the token after that off and we'll call it the label. This would be the target of where we want to branch. And if the operation is of type alphanumeric, in other words, if this token is an alphanumeric, and if the token is a valid branch operation, so here this would be checking to see if it's B or BAL or BNE or all the different condition codes that we could concatenate onto the B. And if the label is an alphanumeric type, in other words, this variable here, which is a token, is of type alphanumeric, and if it's in the label table, then we know it's a valid label. Then what we would do is we would encode the operation. I'm not going to show how to do this, but this is basically what we did in the previous video. So you would turn that into code and you'd be good to go. And then we append that encoded operation to the kernel.img array. In other words, we're keeping track of the last entry in the kernel.img array, and we would then increment that and place the operation in the next slot in the kernel.img array. Now you may have noticed there's a bit of a problem with this label. Is the label in the label table? The problem is that this means that we could only branch to labels that are behind what we've seen already. In other words, if we haven't seen the label, we wouldn't be able to branch to it. So you might ask yourself, how would I solve that problem if I wanted to branch forward to a label I haven't seen yet? And I think you can see that the solution is going to be a second pass through the kernel.img array, where we would have to go through all the labels and update all their targets in the branches. So I'll also leave that as proof to the reader as well. That's kind of a fun problem. But you can imagine keeping a list of labels as you run across them in the branch instructions, and then going back through afterwards and finding those labels in the kernel.img array and fixing those up. Let's take a look at a sample program that our assembler might consume. Here's an example program that does the blinking light LED like we did in the previous video. You'll notice up here that these first few instructions, this is a move immediate. What this does is this takes this value, stuffs it into register 0. Similarly, this move immediate takes this value and stuffs it into register 1. And then I OR registers 0 and 1 and store the result in register 0. This final 0 is how far we want to rotate register 1. You'll be able to see that if you look at the ARM instruction set and you look at the OR instruction there. And the reason I do this is because I can't do a move immediate of the value 2020000 directly into a register using a move. It takes a couple steps. And if you look at once again, the ARM instruction set manual, you'll see that there is no way to get a value like that directly in because of the way the move immediate works with the rotate and so forth. Now, once I have that in register 0, that value is the base address for the GPIO. Then the next thing I want to do is I want to store the value that I need to write to the GPIO controller. And so I can move that directly into register 1. I will do that. I used register 1 up here temporarily and I'm done with it, so I can use register 1 again here now. And then finally, I store immediate, the value that's in register 1, which is this value I just put in here, out to the base address plus 4 here. This is why it's immediate, because I'm adding in this 4 to the base address. And that enables the GPIO controller so that we're able to start writing to turn the LED on and off. Okay, so the next thing I need to do is I'm done with register 1 again, so I'm going to move this value into register 1. This is the value that I need to either turn the LED on or off. And then I store that value that's in register 1 to that base address plus 40 this time. This is where I have to write to turn the LED on. Notice that this instruction is preceded by a loop label here. This is the label for the instructions. So when I want to branch back, I can refer that, and you'll see down here at the very bottom, branch always to loop. That brings me back up here. Now, with these instructions, I'm going to spend some time, just to kill some time while the light's on, the LED's on, and then I'm going to, down here, I'm going to turn the LED off by writing this same value that's in register 1 to the same base address plus 28 this time instead of 40. And by doing that, I turn the LED off. And here I have a similar loop that wastes some more time. The only difference between these two loops is down here I branch if not equal to wait 1 to this label here. Down here I branch to wait 2. And that's the only difference between these loops. You might say, well, why didn't we put that in procedure or subroutine or something? And we'll learn about that in one of the future videos. Let's just walk through this quickly. I store a 0 into register 2 with this move immediate. I add 1 to register 2 and store the result in register 2. So I increment register 2 and I compare register 2 against this, what is this, about 400,000 hex. And so I keep incrementing register 2 every time through the loop, and then finally when I compare these and they're equal, then I won't branch and I'll fall through. So that's how these loops kill some time. This program's a little bit different than standard assembler. This is the assembly grammar that we've defined. And so at this point, if you write this program and you build your assembler, you ought to be able to translate this program into a kernel.img that you can then run on your Raspberry Pi and see your LED blink. This brings us to the end of another video. I'm sorry this one turned out to be a little bit long again. I apologize for that. There's just a lot of ground to cover. This is pretty exciting stuff though. I hope you enjoy writing your assembler. It's a fun little challenging program. It'll take a little bit of effort, but I think I've given you enough that you'll be able to work your way through it and figure it out. Remember, if you have questions about these videos and you'd like me to address them in future videos, or if you just like maybe some help or some pointers or something like that, you can contact me at somepiguy@gmail.com. I look forward to talking with you in a future video.